Okay, so far, we have been discussing random sequences. A very important concept in that context is that of stochastic convergence. That is, classically you have seen in mathematics, that if you are given a sequence x of n, then we immediately talk about its convergence, whether it converges to something or not. Similarly, if you are given a random sequence, that is a sequence of random variables, obviously same question can come again, that is whether it converges to some point something or not, and if so, what is the notion of convergence here? Because it is not just a sequence of numbers, it is a sequence of random variables which take various values depending on your experiment, right? So, what will be the notion of convergence here? This is very important. Okay, to get into this, in fact, we will not be discussing that today, but just to develop the motivation for this, how these notions are developed. Okay, just to get a motivation for this topic, we will start at a topic, an issue which maybe I should have considered earlier, but I didn't. I kept it for this lecture. Okay, it is called now, suppose you are given a random variable x, okay, x is a random variable, expected value of say x is say mu, and expected value of x minus mu whole square, which is the variance, is a sigma square. Now, what does this mean? That you first form a random variable x minus mu and square it up, you can call it x prime, then E of x prime is sigma square, right. Now, you can see it means that on a line, suppose this is the origin, now x prime, its minimum value can be 0. X can be to the right of mu, to the left of mu, that is x minus mu can be positive or negative, but square of x minus mu, which is x prime, that is always positive or 0, it can never be negative. So, its minimum value is 0, that is when x equal to mu, and as x deviates from mu either to the right or to the left, x prime, the value of x prime increases. Okay, so, it goes up like this. As x takes further and further values, goes further and further away from mean mu, its value increases. So, expected value of x prime could be somewhere here, suppose, okay, and that is, if I give it to the square, if you, that is sigma square. Okay. Now, what does that mean? That if I am observing x, then this difference x minus mu square, it will take values around sigma square, right. So, in some experiments x prime can take value to the left of sigma square, in some experiment to the right of sigma square. So, its concentration is around sigma square. To the left hand side it can go only up to 0, that means to the right hand side also it will not go up to infinity, because then the average cannot be sigma square, a finite number. So, on either side it can go over a range like this. Okay. Then my claim is, like this. So, then my statement is, if sigma square or rather sigma, both are positive, is a small quantity, that means if suppose you have a situation like this, sigma square is only this much, then I can roughly have a range like this around sigma square, right, for x prime, which means x minus mu, this variable x prime, in fact x prime is x minus mu square, will vary over a small range around sigma square. So, physically this means that if I am now coming back to the random variable x, and I am measuring x in the experiment after experiment, I am getting values close to mu, because the deviation x minus mu, okay, it will be over a small range. It can be positive or negative, but its range cannot be much, because square of x minus mu, which is x prime, okay, its mean is much less, which is sigma square, that is much less, which means x minus mu, there is a deviation of x around mu, okay, will be in a very small range. That means, if sigma square is really small, then if we measure x, we can say that our measurements for x, they are all coming across mu, close to mu. So, loosely you can take even the particular measured value to be an estimate of mu. Okay. In this context, an inequality comes to be of help. There is this Thebycheff inequality. It says that probability of this deviation, its mod, that is either to the right or to the left, whether the deviation across mu is positive or negative, but the mod value, there is a magnitude of the deviation. If this is greater than equal to some positive constant epsilon, epsilon is greater than 0. Epsilon is going to be greater than 0. Okay. So, probability that this deviation has magnitude greater than equal to epsilon is always less than equal to sigma square by your epsilon square. That means, if sigma is much less compared to epsilon, that is the variance of x is around the x is less, and the epsilon, there is a range of deviation that we are choosing is comparatively larger, then the probability that the magnitude of the deviation will be higher than epsilon, that is x will indeed go beyond mu plus epsilon or mu minus epsilon, will be very small, because sigma square by epsilon square is small. I will again come to this point, but first let us prove it. Now, what is this? What is this? This will be equal to two integrals. X minus mu greater than equal to epsilon means, that is x minus mu mod greater than equal to epsilon means either x minus mu greater than equal to epsilon means that is either x minus mu greater than equal to epsilon. Epsilon is positive, so I am considering positive deviation, that is deviation to the right of mean mu. So, x minus mu in that case greater than equal to epsilon, meaning either x greater than equal to mu plus epsilon, or if the deviation is negative, that is x is taking value to the value less than mu. So, deviation is to the left of mu. In that case, this is less than equal to minus epsilon. Okay. Either the deviation is greater than plus epsilon, greater than equal to, or less than equal to minus epsilon. In this case, you get x less than equal to minus mu minus epsilon. So, what is the probability that x takes values either greater than equal to mu plus epsilon or values less than equal to minus mu minus epsilon? Sorry, plus mu, this would be plus mu minus epsilon, either greater than equal to mu plus epsilon or less than equal to mu minus epsilon. Okay. So, there should be two integrals, one from minus infinity to infinity, minus infinity to mu minus epsilon If you see Papolis's book, there is a mistake here. He puts a minus symbol with mu. That is wrong. It will be mu minus epsilon px, which is the probability density of x dx, and there is another integral mu plus epsilon up to infinity px dx. Okay. Now, we keep this result. Okay. This we keep somewhere. Okay. That is, I repeat here just for storing purpose, that is probability of x minus mu greater than equal to epsilon is nothing but minus infinity mu minus epsilon px dx plus mu plus epsilon infinity px dx. Okay, this result we keep separately. Now we consider sigma square. What is sigma square? X minus mu whole square, its expected value. So, this is multiplied by px dx integrated. So, obviously, since x minus mu square, mu whole square is positive, p of x is a positive non-negative number. This is, I mean, all are non-negative. X minus mu whole square, p of x, okay, these are non-negative, and dx is of course always positive. Okay, this is this integral obviously is greater than equal to same integral, but over a shorter range, over a reduced range. That is from minus infinity to say mu minus epsilon x minus mu whole square px dx plus okay. Earlier we are going from minus infinity to infinity. Now we go from minus infinity only up to mu minus epsilon, and again jump over a region and start again at mu plus epsilon and go to infinity. So, it is a reduced range. Okay. So, obviously, the value, since all the quantities being integrated are positive, the net value of the integral on the right hand side of the two integrals summed added, that will be less than equal to sigma square. Okay. Now, in the first integral consider, or maybe in the second integral to start with, you consider x minus mu whole square, this function. As x takes value mu plus epsilon, I get only epsilon square, mu cancels, plus mu minus mu cancels, I get only epsilon square px dx. Then as x takes values still higher and higher, x minus mu whole square, that also takes values larger and larger, that is higher and still higher than the original, I mean the starting value of epsilon square. Right, I repeat again, the starting value of x is the lower limit, that is mu plus epsilon. If you put mu plus epsilon here, plus mu and minus mu cancels, and you are left with epsilon square, but as x increases further, so you put values here which is not just mu plus epsilon, but something more. So, obviously, maybe delta, so mu plus epsilon plus a delta. If you put that here, you get epsilon plus delta whole square, which is greater than epsilon square. That means this integral is less than equal to, this second integral is less than equal to mu plus epsilon up to infinity px dx, because while this function x minus mu whole square takes higher and higher value as x goes from mu plus epsilon up to infinity, I am holding this fixed at epsilon square. I am not allowing this quantity to go beyond epsilon square here. So, obviously, net value that we get by this calculation will be less than what I get by this integral here. In this integral, this function x minus mu square is increasing function, but here I kept it fixed at epsilon square, which is the minimum value, and integrate the rest. So, obviously, net value, net thing that we will get is less than what this integral would give. Same way, you consider the first integral. When x takes the upper limit, mu minus epsilon, mu cancels, minus epsilon whole square, which is epsilon square. But as x takes values less than that, maybe mu minus epsilon minus delta. If you put that here, you get minus epsilon minus delta whole square, which is higher than the original starting value of epsilon square, right. So, as x takes lesser and lesser values and goes up to minus infinity, this function x minus mu square goes on increasing. So, if I consider only epsilon square for it and integrate the rest, then obviously I will get a lesser value. That means this integral is less than epsilon square So, here you take epsilon square common. Okay, here you take epsilon square common. So, what you are left with is simply what we wrote at the top. Okay, that is, this is nothing but epsilon square into probability of x minus mu mod greater than equal to epsilon, which you wrote at the top. Okay. So, obviously, probability of mod of x minus mu greater than equal to epsilon is nothing but less than equal to sigma square by epsilon square. That is, sorry. This is the Thebycheff inequality. You remember, this is what we wanted to prove. Okay. So, what is the significance of this? That is, suppose x is varying across mu, but sigma, that is the, if you take really x minus mu, okay, and square it up and take the average, that average value is sigma square. Okay, that means, and if the sigma square is much less, that means if this corresponds to sigma square, okay, that means, or sigma rather, because sigma, when I take sigma square, it is x minus mu whole square, but here it is, the x is for x. Okay, so around this, if sigma square is much less, then we get values of x in most of our trials around mu in a small zone. It does not go far to the right, far to the left. And if you now take an epsilon like this much, which is much greater than, this much greater than sigma, obviously this inequality means that the probability that x minus mu is either, there is a deviation of x minus mu is either greater than or equal to epsilon, that is, x takes values to the right of this, that is, x is either greater than or equal to mu plus epsilon, that is, takes values on this side, or to the left, that is, takes values to the left, this side, that is, x is less than or equal to mu minus epsilon. probability of that will be much less, almost like almost close to 0, because sigma square is given to be much less than epsilon. So, sigma square by epsilon square is almost equal to 0. So, obviously this implies that probability that x takes values far away from mu on either side, that is x takes values either to the right of mu plus epsilon or to the left of mu minus epsilon, that will be very, very less, almost 0, if the epsilon chosen is much greater than sigma. Okay, so, what we have been discussing physically, that comes through this inequality also. Few things we can see. Suppose x is such a random variable, it is given that E of x is mu, okay, but sigma square, which is E of, suppose it is given to be 0. Okay, that x is such a random variable whose mean is mu, but whose variance is given to be 0. Then that means for any, I underline this, for any epsilon greater than 0, probability of, I write it in expander, x minus mu, sorry, just a minute. Which is also equivalent to probability of x taking values either greater than equal to, that is when x minus mu is positive, the deviation is to the right of mu, this is greater than equal to mu plus epsilon, this set union with x taking values to the left of mu, that is mu minus epsilon, that is x taking values to the right of mu plus epsilon and to the left of mu minus epsilon. For any epsilon, this is by the Thebycheff inequality less than equal to sigma square by epsilon square, but sigma is given to be 0 and epsilon however small is non-zero. So, this is equal to 0. That this means what? That x is such a random variable that it always takes the value mu with probability 1, because for any epsilon chosen, its probability of taking values higher than, greater than equal to x minus mu and less than equal to x minus mu, sorry, greater than equal to x minus epsilon, greater than equal to mu minus epsilon and mu plus epsilon, or less than equal to mu minus epsilon. That is graphically it means there is, if your mu is here and epsilon, for any choice of epsilon, probability of x taking value to the right this side or to the left, that is 0. And you know this is true for any epsilon greater than 0 however small. So, you now start letting epsilon tend to 0. Obviously, from right hand side and from left hand side we will be approaching mu. Okay. So, as long as you are not at mu, but very close to mu on the left hand side and right hand side, probability of x taking those values is 0. Okay. You can let this limit tend to, this epsilon tend to 0. This obviously means the probability of x taking value mu is 1. Okay. So, we say that x takes the value mu, x is such a random variable that it takes the value mu with probability 1. Okay. And its variance is 0. Further, suppose x is a random variable and E of x square, which is always, this is always true, mu square plus sigma square. okay, that is expected value of x square, which is also called the expected power in electrical engineering language, is expected power of x. And suppose this is given to be 0. Since this is a squared number, this is a squared number, and therefore both are positive, this means mu is equal to 0, sigma is equal to 0. Now, sigma equal to 0 means x is such a random variable that takes the value mu with probability 1. That means in all experiments you will continue to get the value of x equal to mu. And what is mu here? 0. So, that means x is a random variable which will always take the value 0, okay, with probability 1. You remember when we were discussing this vector space of random variables, then in that vector space we also considered a 0 random variable, we called it 0 vector. And that time I made this statement that is such a vector, that is such a random variable which always takes the value 0 with probability 1. I mean, this explains that further. Okay. Secondly, if you consider this bound, now you know this provides an upper bound, that is this probability should be less than or equal to this, but sometimes this upper bound may be much higher than the exact probability. You choose some epsilon, you are giving the probability density function of x, from that you can carry out calculation and find out the exact value of this probability, and you can find, you will sometimes find that this is actually much less than sigma square by epsilon square. So, this you could keep in mind. This is just a bound, it shows that this left hand side can never exceed the right hand side, but it no way means that this will be close to sigma square by epsilon square. In some cases yes, but in many cases no. For example, if suppose it is given, suppose x is given to be Gaussian or normal, this is Gaussian, in that case Gaussian, mean mu and variance sigma square, you know what is this probability density, 1 by root 2 pi sigma e to the power minus x minus mu whole square by twice sigma square. If this is given, then you can find out yourself that if you choose epsilon to be just 3 sigma, that exact value will be given by I am directly quoting from Papoulis, this. But what does the right hand side, this bound gives? Sigma square by epsilon square in this case, epsilon is 3 sigma, so sigma square by 9 sigma square, which is 1 by 9, and 1 by 9 is close to 0.1, which is much higher than this. So, let us remember this probability, this left hand side is always less than or equal to the right hand side. So, right hand side is a bound, but it does not mean that left hand side is close to it. In fact, left hand side, this probability as such can be very small compared to the right hand side. It will depend entirely on the probability density function given to you and the epsilon that you choose and all that. Okay. Only importance of this, main importance of this bound is that this is independent of the probability density function that is applicable to the x, because this bound is always satisfied by any random variable of any arbitrary probability density function. Okay. Now, consider a more general result. Suppose this is given that x random variable, but p of x equal to 0 for x less than, less than 0, not less than equal to. That means x always takes values either 0 or positive, or x always takes positive values which are either positive or 0. X is always non-negative. Okay. In that case, then for any alpha greater than 0, this alpha you choose, some positive number you choose, probability of x taking values greater than equal to alpha is always less than equal to mu by alpha, where mu is the mean of x. This is interesting, there is no sigma here. Please see the difference in this result. I am only considering random variables which take non-negative values, that is either 0 or positive numbers, that is p of x is 0 for x less than 0. In that case, I am saying that if you now choose any alpha which is positive, then the probability that x takes values greater than equal to alpha is simply less than equal to mu by alpha. So, in this relation there is no variance that is coming into operation. Okay. But this is a more general result, we will come to that soon. How to show this? Proof is very simple. What is mu? Mu is E of x. What is E of x? X into Px dx. Okay. But integral should not be from minus infinity to infinity, it should be from actually 0 to infinity. So, I correct it to 0 to infinity. Now, remember within this range 0 to infinity, x is taking always values which are positive or 0, and p of x is always non-negative. Okay. So, that is integral is always positive, and this product x into px is always positive, and that is being integrated. Of course, the result is positive, mu is positive, has to be. Then this means if we now do the integral from alpha, there is sometimes some confusion between alpha and infinity. So, this is alpha and this is infinity. Okay. The alpha to infinity, where alpha is positive, if we just carry out this integral, then this must be less than equal to the previous integral, which was over a larger range from 0 to infinity, isn't it? So, this is less than equal to the previous one. And now, within this integral, we look at the function x. It starts at alpha, some positive number, and goes up to infinity, and multiplied by the respective value of px. Now, if instead, if you do not allow x to go up, but you hold it at alpha only, but let px continue as x moves from that is, we carry out an integral like this, where as far as this function p of x is concerned, we let x move from alpha to infinity, but as far as the x in the previous integral is concerned, we do not allow it to vary from alpha to infinity, we hold it at its minimum value alpha. Then obviously, the integral will be, since everything is positive, the integral now will be less in value than the previous integral, because earlier both x and px were multiplied and integrated. X was first taking value alpha and then going up. But now I am multiplying px only by alpha. Okay. Even if x is varying from alpha to infinity, Px is multiplied only by alpha all along, not by some quantity which is becoming higher and higher. So obviously the net value of the integral will go down. So this will be further less than equal to this and outside alpha. By the way, if I ask you why I am putting less than equal to and not less than in both cases, answer is just for mathematical correctness. For instance, initially I said that x into px dx integrated from 0 to infinity, that should be greater than equal to the same integral but from alpha to infinity. Why greater than equal to? Because it may so happen that your probability density function p of x is chosen such that from 0 to alpha its value is 0. So obviously the integral itself becomes identical to this next integral, that is x px dx from alpha to infinity, because in the range between 0 to infinity p of x is 0, so no point in carrying out the integral there, it will take the 0 values. In that case equality will remain, will be preserved. And further in that case, and then here how you can take alpha out? It may so happen in a defined context that as you go beyond alpha, px comes down to 0. In that case, whether x is increasing or x is kept at alpha, it hardly matters. Okay, that is why it is less than equal to. Okay. And what is p of x dx from alpha to infinity? This side is then equal to alpha into, this is nothing but probability of x taking values greater than equal to alpha. That is why you integrate px with respect to x from alpha to infinity. That will give you the total probability of x taking values greater than or equal to alpha. So that proves the inequality, that is now suppose as a random variable a given number, given constant n given integer. You consider a random variable x prime, which is nothing but say mod of x minus a whole to the power n. So obviously mod of x prime is a random variable that takes only positive values. Okay, that takes only positive values. That means I can apply the above result if I choose, that is the above means then that for any epsilon greater than 0, any positive number, positive epsilon greater than 0, I can write from this that probability of this random variable x minus a whole to the power n, this is a random variable, I call it x prime. This is greater than equal to epsilon to the power n. That should be from this result less than equal to expected value of this random variable x prime divided by epsilon to the power n. Okay, that is expected value of this random variable x prime, that is x minus a mod to the power n, like here expected value of x was mu. Now the random variable is x prime, which is equal to mod of x minus a to the power n. So I am taking the expected value of that divided by the quantity to the right of this greater than equal to sign. Earlier it was alpha, so alpha came as the denominator. Now it is epsilon to the power n, so it will be epsilon to the power n. Okay. What does that mean? This is fine, but my claim is probability of actually let me write in a more elaborated way. It is not probability. The event, this event is identical to the event this is because whether you take mod of x minus a or mod of x minus a to the power n, mod of x minus a is always positive, epsilon is positive. So if it is giving that mod of x minus a whole to the power n is greater than or equal to epsilon n, it obviously means, since the quantities are positive, it obviously means mod of, and n is a positive, n is a number, n is an integer, it does not matter whether it is positive or negative though. Essential thing is that mod of x minus a and epsilon both are positive. If the above inequality is given that mod of x minus a whole to the power n is greater than or equal to epsilon to the power n, this obviously means mod of x minus a is greater than or equal to epsilon. Conversely, if this is given that mod of x minus a is greater than or equal to epsilon, obviously if you raise the both left hand side and right hand side to any power n, since both are positive, both mod of x minus a and epsilon are positive, if you raise to any power, even then left hand side will be greater than or equal to right hand side. So the two events are same. Okay, one implies the other. That means from above I can also write that probability of so you see this is interesting. In the Thebycheff inequality, our left hand side was this, only a was replaced by mu, okay, but this is more general, p of probability of mod x minus a greater than or equal to epsilon, okay. But on the right hand side, you are free to choose n, but left hand side then is always less than or equal to right hand side for any n. So you can put n equal to 1, still it is satisfied, you can put n equal to 2, still it is satisfied, and so on and so forth. Okay. You can now see that if you take n equal to 2, okay, if you take n equal to 2 and a equal to mu, that is x is, I mean a is the mu, a equal to mu, that is the mean of x. In that case, you simply get back your Thebycheff inequality, right? So this is much more general result. Okay. Now, in the limited time that is left, I will just introduce, I will just get into the concept of, I will just start this discussion on stochastic convergence as convergence of random sequences, but again, I will again need some further discussions before I can take that up. You know, this given a random sequence, I mean Finding out a notion of its convergence is a fundamental problem in theory of probability, as I told in the beginning. Okay. So, we again try to develop these notions using those Thebycheff inequality and related concepts here. Suppose you are just conducting a very simple experiment, you are measuring the length of something, okay, and actual length is maybe A, but what you are getting is not A, but you are getting some error in our communication or electrical engineering language, we call it noise. So, what you are measuring, what you are observing is x, which is not equal to A. A is the actual length, it is not known to you, it is unknown. You are trying to find out what is actually A. Unfortunately, every time you measure, you get some different readings, and this is A plus V. V actually is just a random error, okay, it is like your noise. It is not a systematic error. If it is a systematic error, it can be corrected, or at least it is deterministic, so it can be subtracted. It is not in your hand, it is just a random thing. So, it is like a noise term or error term, random error term. Okay. So, x is equal to A plus V. So, instead of finding out A, you are only getting x. Okay. Then you can easily see from our previous discussion and from here that if V is such a random variable, V is a random variable such that its variance is much less, then x will be close to A always. This is what we have elaborated so far in our discussion. A was that time mu. Okay. That means the x minus mu, the deviation, will not go far. Okay, will be within some small range around mu, because V is the variance of V or variance of x minus A, or even variance of x, that is much less. Okay. In fact, from Thebycheff inequality we saw that suppose it is given, that is it is given that E of V square is sigma square, and if it is given that sigma is much less than some number epsilon, which is again much less than A, that is sigma is much less than A, and you can find out again some number epsilon in between, so that sigma is itself is much less than epsilon, which is again much less than A. You can then write using Thebycheff inequality that probability of less than equal to, okay, that time we consider it to be greater than equal to, now we consider it, it is not necessary, greater than epsilon, which is nothing but 1 minus this is sorry okay. And obviously, this is, I mean, this thing probability of mod x minus a greater than equal to epsilon was less than equal to sigma square by epsilon square. So, you put a negative sign. So, less than equal to becomes greater than equal to, and add 1. So, greater than equal to simply becomes greater. So, this is nothing but greater than sigma square by epsilon square. Okay. And since sigma is much less than epsilon, what it means that x minus A that is sorry, this will mean that x will be in this range with high probability. There is a probability will be, probability of that will be greater than 1 minus this, just a minute, there is a mistake here, I left out one term. That will be greater than equal to 1 minus this. Since sigma is much less than epsilon, this is almost close to 1, but of course probability cannot exceed 1. This is always less than equal to 1 from left hand side. But if sigma is really very close to, very much less than epsilon square, this is just 1 minus some very small amount, 0.000 something, okay. So we can loosely say, using probabilistic language, that x will almost certainly, almost surely be within a range a plus epsilon to a minus epsilon. And since epsilon itself is much less than a, as I told in the beginning, as I assumed, x will be then in a very small, I mean x will be very close to a, or almost equal, almost close to a. So in that case, it will be safe to take the particular x that you measured as a good estimate of a. You don't have to repeat the experiment again and again. Okay, you don't have to look for further trials, because if sigma square is less than epsilon square, if sigma square is less than epsilon square, this itself is very close to 1 then, because this is less than, this is almost 0. So this probability is between 1 and some quantity which is very close to 1. So we say that x is almost certainly within this range, a plus epsilon to a minus epsilon, and since again epsilon is much less than a, x is within a plus to a minus, we can say. So whatever x you get, you can simply take it to the estimate of a, no problem. But suppose this is not true, that sigma square is not really, or sigma is not really much less than a. So you cannot apply this. Then what do you do? That is where the sequence of random variable comes actually. Then suppose we perform the experiment several times, n times. First time you get x1. First time whatever you observe, you give it a name, random variable x1. Then you observe x2. Then you observe x3. So you get a sequence of RVs, random variables, x1, x2, dot dot dot, maybe xn, xi, outcome of ith experiment. Okay, these experiments, and xi is equal to a plus some noise term during the ith experiment, the noise term that comes, that is Vi. So actually if you again repeat the experiments, first, I mean, see you are making n observations, x1, x2, xn. After half an hour maybe you can make again another n observations. So in the first observation Vi took some value, next time ith step you will get some other value of Vi. In that sense Vi is a random variable, okay, of variance sigma I. Okay. In fact, to make life simple, you can assume that Vi, whether it is V1 or V2 or Vn, they all have the same variance. After all, it all is coming from the same error process. Okay. And now, after making n trials, that is, you got some values for this n random variables out of this sequence of your x trials. First trial x1, you got the value of x1, then x2, then xn you measured. Okay, this together consists of one experiment. Next time again you measure x1, x2, xn, and likewise. But I am just bothered about only one experiment. Then you measured some value of x1 only, x2 and xn and stopped. You are not measuring again. And what you are doing, you are finding out a sample estimate, which is then again a random variable. Now obviously what is the mean of this? Mean of xi is a, because Vi is 0 mean. Maybe I forgot to mention that this error, it can take positive value or negative value, its mean is 0. That means each xi has a mean a. So what is the mean of x bar? Mean here, that is a, then mean here, that is a, n n times n into a divided by n. So, E of x bar is same as your a, but what is x bar minus a whole square? Variance, that will be, you can see, sigma square by n square. That is the beauty, okay. Sigma square by, sorry, n, not n square, n. So, variance is coming down, okay. Earlier it was sigma square, and I said if sigma is not much less than a, we have a problem. We cannot simply measure once and take it to a good estimate of a. In that case, I measure it n times and take a sample average. This sample average, if I call it a random variable, its variance is not sigma square, but sigma square by n. And if sigma square by n, sorry, I am about to finish, just 1 minute. If this is much less than a square, because it is sigma square, suppose it is much less than this, then obviously we can invoke that inequality, okay. If it is much less than a square, then whatever value of x bar you measure by the sample average, that is good enough. That will be close to the mean A, because variance, okay, what does it mean? The variance, new variance, if you call it sigma prime, which is nothing but sigma, sorry, square root of sigma square by n, okay, and what is mean? Mean is A. So, that means this ratio is much less than 1, okay. So, I can use that previous theory and I can say that probability of less than equal to or maybe less than some epsilon is almost close to 1. So, whatever value you measure for x bar, that is good enough. So, that is all for today. So, next class we go further into these notions. Thank you very much.